Section 11.3.1, assume that both populations are normally distributed. Here we have sample 1 that has a sample size of 21, sample mean of 18.3, sample standard deviation of 4.1. Sample 2 has a sample size of 21, sample mean of 14.7, and a sample standard deviation of 4.5. Now in part A, we want to be able to test whether population mean 1 is not equal to population mean 2 at the alpha equals 0.05 level of significance for the given sample data. Okay, so we are assuming that both populations are normally distributed, so we don't need to figure out the requirements, but we do want to start out with the null and the alternative hypothesis. Okay, well, we want to write that down because we want to know that the not equals is always going to be in the alternative. So that means population mean 1 is going to not equal population mean 2. And the null hypothesis always contains the equality, so therefore population mean 1 is going to equal population mean 2. Step 2. Now we got to determine what kind of a tail this is. Okay, well, since it's not equal, that tells us that we have a two-tailed test. And then what we need to do is we need to write down what is a significance level. And a significance level is given to be 0.05. Okay, now what we want to do is we want to find the test statistic. Okay, so here is the formula for the test statistic. We want to write down the given information for this. So the given information is given right here. We know that the sample size for population 1 is 21. We know that the mean for population 1, or the sample mean, is 18.3. And we know that the sample standard deviation for population 1 is 4.1. For population 2, we know the sample size is 21. We know that the sample mean for population 2 is 14.7. And the sample standard deviation is equal to 4.5. Okay, and now we need to solve for mu1 minus mu2. Well, we know that in the null, we know that mu1 is equal to mu2. If we subtract mu2 to both sides, that means mu1 minus mu2 is now going to equal 0. Now that we have this information, we can now go ahead and then find the test statistic. So we have population mean 1, which is 18.3, minus population mean 2, which is 14.7, minus mu1 minus mu2, which we know is 0, divided by the square root of standard deviation 1 squared over the sample size, which is 21, plus standard deviation 2, which is 4.5 squared over 21. Okay, so now we're going to put this in our calculator. So my recommendation is to put parentheses around this so that we don't have any problems with order of operations. So let's go ahead and do that. In our numerator, we have 18.3 minus 14.7, and that's minus 0, so we can just hit enter. It gives a 3.6 in the numerator. Then we're going to divide that by the denominator. So we're going to hit second square root. In the first part, we're going to put parentheses 4.1 squared, and then we're going to divide that by 21. And then it's going to be plus, we have 4.5 squared, and then we're also dividing that by 21. Close the parentheses, and then we're going to hit enter. And then let's go ahead and then copy that number. Okay, so now we have that number. And now we want to simplify that or round it to 2 decimal places. So the test statistic is going to be 2.71. Now for this example, we need to use the t-distribution to find the p-value. And now the p-value is not going to be exact. But before we do that, let's draw our picture so that we know kind of what this p-value is going to look like. okay, because it's really important to see what the picture looks like. So we have our bell curve. Okay, and then we have our mean, which is 0, okay? And so what that means here is that we have a test statistic. And our test statistic we have at 2.71. And we have another one here at negative 2.71, which gives us two areas, which is the reason why we get a two-tail. So this is our p-value. So our p-value is containing two regions here. Okay, but we're going to use the t-distribution over here. Okay, so first thing we need to do is we need to figure out, okay, what are the degrees of freedom? Okay, well, we could use the formula that's given, and that formula is this formula here where you're using it to find the degrees of freedom. But for the purpose of this particular exercise, we're going to find the degrees of freedom by taking the smaller of the two. Okay, so what we're going to do is, instead of using this formula, okay, we're going to take a look at the two sample sizes. Well, they're both 21, so neither of them are smaller than the other, so we're just going to take 21, and we're going to subtract 1 to get 20. Okay, and then we got to use the test statistic, which is 2.71. So what we're going to do is we're going to come down here, we're going to look for the degrees of freedom, which is 20. Okay, so here's our degrees of freedom. Okay, so here's our degrees of freedom, and then what we want to do is we want to look for the number of 2.71. So where is 2.71? Well, 2.71 is in between 2.528 and 2.845. So what that tells us is the following. That tells us that the p-value is going to be in between these two numbers up here. It's going to be in between 0.01 and 0.005. So when we write the p-value, we will then say that the p-value is going to be in between those two numbers. The smallest of the number is 0.005, and the other is 0.01. Okay, now because this is a two-tailed, right? Because it's two-tailed, okay, that means that we need to multiply both of these p-values times 2. So if we multiply those by 2, we're going to get 0.01, which is less than or equal to the p-value, and this is going to be 0.02. Okay. Okay, so now in this example, let's look at our options. Okay, so if we take a look at what we got here, okay, we're going to use this information to determine the range of the p-values that are relative to the most common values of alpha. And these are the most common values of alpha. And so if we take a look at A, B, C, or D, which one does it represent? Well, we can say that it represents A. Okay, so what does that tell us? Well, that tells us that if we look at this entire p-value, if it's in between 0.01 and 0.05, okay, that is actually, if we compare this p-value with alpha, and alpha in our problem is 0.05, that means that it's going to be less. So we know that that value is going to be less if it is in between there. Okay, so if it is less, then what we're going to say now is we're going to reject the null hypothesis because the p-value is less than or equal to the level of significance. Okay, now the second part of this question is asking us to be able to construct a 95% confidence interval about the population mean 1 minus population mean 2. So let's go ahead and then copy down this information that we have here. Okay, so this is our data that we're given. Okay, so to find the lower bound, to find the upper bound, we need that information, but we also need to find the critical value. Okay, so the critical value, we need to first take a look at alpha, and alpha is equal to 1 minus 95%, which is 0.95, which gives us 0.05. Okay, and then we need to take alpha and then divide that by 2, which gives us 0.05, divide that by 2, which gives us 0.025. Okay, and then we also need to determine, okay, what is the degrees of freedom? Okay, so the degrees of freedom, again from our previous step, is 21 minus 1, which is 20. So let's find that critical value. So we know that we have an area of 0.025 and the degrees of freedom, which is 20. So we will see that our critical value is the following. We get the critical value of 2.086. So the critical t value is 2.086. And now we can plug in our information to find the lower and the upper bound. Okay, so let's find a lower bound. The lower bound is going to equal the mean 1, which is 18.3, minus mean 2, which is 14.7, minus the critical value of 2.086 times the square root of standard deviation for 1 squared over the sample size of 21 plus 4.5 squared over 21. Okay, so now we can go ahead and then put this into our calculator. So we're going to do this according to order of operations. So doing this according to order of operations, we're going to start with what we have here. So we're going to take 4.1, we're going to square it, and then divide that by 21, and then hit equals. And then we're going to add, we'll put this in parentheses, 4.5 squared, divide that by 21, and then hit enter. Okay, now this is what's under the radical, so we have to take the square root of this answer. So we're going to hit second square root, second answer, hit enter. And now we're going to multiply it by negative 2.086. So times negative 2.086. And then we're going to add 18.3 that's in parentheses minus the 14.7 in parentheses. And therefore we get the following number. Okay, now we're going to round this to 2 decimal places, so we get 0.83. Okay, and so now we're going to do something similar there with the upper bound. So let me go ahead and copy this. Okay, and then there's a couple things that we're going to change here. So we're looking for the upper bound, and this is going to be a plus. So we're looking for the upper bound, and we know that we're going to add here. So let's go ahead and do the same thing. So we have the following. Okay, we can go back and we can find this answer here where we took the square root of the answer. And what's nice about that is with the calculator, we can come back up here and just hit enter, what we highlighted. And that gives us exactly what was in here when you take the square root of it. And now we're going to multiply it by positive 2.086. And then we're going to add, again, parentheses, 18.3 minus 14.7, close the parentheses, and then hit enter. And therefore, now we're going to get that number. So we can round this to 2 decimal places, and this becomes 6.37. So then we can say the following. We can say that the 95% confidence interval is the range from 0.83 to 6.37.